All right, let's get started. So welcome to our second Bootstrap Parallel section. So our first speaker is Shai, and he's going to talk about bootstrapping string and M theory. Please.
Hi, thanks for the invitation and introduction. So this is based on a paper from last year as well as an upcoming paper that should be out hopefully in the next month or so. So what is non-perturbative string theory? So usually we define string theory using the world sheet, and that only allows us to compute things perturbatively in the string couplet. But ideally, we would like to understand string theory non-perturbatively, because most of the most interesting aspects of string theory, like eventually if we want to use it to actually describe the real world, we're going to have to understand it non-perturbatively. You know, for instance, if we want to do things like flux compactification or stuff in de Sitter, etc. Unfortunately, the only non-perturbative definition of string theory that we have so far is from holography. So in particular, the classic examples that everyone's probably familiar with is you could have type 2b string theory on ADS5 crosses 5. That's dual to n equals 4 super Yang-Mills. With the standard dictionary where you relate the complexified coupling in Yang-Mills to the complexified coupling in type 2b. And then n is related to the string length as follows. The other classic example of ADS-CFT, probably the next simplest case, is M theory in ADS4 cross 7 mod CK. It's dual to a certain three-dimensional CFT called ABJM. The reason why these are the two simplest cases is because they are the two cases that have maximal supersymmetry. Of course, there's also the example in 60, but we won't talk about that in today's talk. And here too, we have this ADS-CFT dictionary where again, n is inversely related to the Planck length. So in the ADS-CFT dictionary, graviton scattering on ADS is related to the stress tensor correlator in the CFT. And so this holographic description is pretty much the only way we know how to define non-perturbative string theory to date. And so if we want to learn about non-perturbative string theory, we pretty much have to use holography, at least so far. So the thing is that ADS-CFT is only half the story, because ADS-CFT takes the very challenging problem of quantum gravity and it turns it into the slightly less challenging problem of CFT. But CFT is not a solved problem because when it's strongly coupled, you can't use standard methods like Feynman diagrams. And so you need a non-perturbative approach to CFT in order to non-perturbatively understand string theory, which is what we're going to discuss today. Now, there are other ways people have attempted to study these holographic CFTs prior to Bootstrap. So for instance, at leading order in the large N expansion, which is dual to the classical string theory, there's something called integrability, which allows you to study quantities at finite top coupling. But so far, integrability has only been developed in the planar limit. And so you can't use it to study the quantum string, which would be one of our n corrections. Similarly, you can't use it to study M theory, because there just simply is no planar limit in that case. Similarly, at least in the case of super Yang-Mills, there's a weak coupling limit, so then you can just do Feynman diagrams. But that's kind of the opposite limit of what you care about if you're interested in gravity, because that's like in the very stringy regime, not in the gravitational regime. So if you want to study the proper gravitational regime, one of our n corrections, you really need methods other than integrability or just Feynman diagrams. So today we're going to combine the three non-perturbative constraints that are known today in order to study these holographic CFTs and thus to non-perturbatively study quantum gravity. So the three non-perturbative constraints we're going to use are unitarity, which in the context of today's talk is basically that OP coefficients are real and their scaling dimensions are bounded. We're going to use crossing symmetry, which we're going to combine with unitarity in order to do the standard numerical bootstrap algorithm. And then finally, we're going to use supersymmetric localization, which will allow us to input protected coupling-dependent quantities to the bootstrap, which is very important to actually isolate these theories. Okay, so let's start with n equals 4 super Yang-Mills. So we're going to consider the stress tensor correlator. We look at the superprimary S. Kinematically, you expand it as follows, where basically all the non-trivial data in this 4-point function is the scaling dimensions and spins of the long multiplets in the singlet representation. So this is all we care about, these lambdas and deltas. The way you specify an n equals 4 theory is by the value of c, which is basically proportional to n squared, as well as the value of tau, which parameterizes the conformal manifold, because all n equals 4 CFTs are conformal manifolds. And so as long as you tell the theory what tau is and what c is, you have uniquely specified the theory, and all data is a function of tau and c. So the localization constraints, these are non-perturbative constraints, and so the way they relate to the 4-point function was worked out in these papers from a few years ago. Basically, you take the mass of form free energy, where this is the mass for the hypermultiplet, you take derivatives of the mass, set the mass to 0. For the first constraint, you also take derivatives of tau, and as long as you're taking 4 derivatives, this relates to the 4-point function. And the reason is because each derivative brings down the operator which it couples to, which is the stress tensor multiple. So the precise forms of these integrals I won't tell you because it's not so important, but like they are known. And you can see this will constrain the 4-point function in terms of this block expansion. So the power of this relation is that the left-hand side can be computed exactly as a function of tau using supersymmetric localization. Because this partition function can be written as an n-dimensional matrix model integral. And in fact, over the years, we figured out how to compute this n-dimensional matrix model integral essentially exactly. So for the first constraint, just the full exact formula is known, which is worked out by Michael Green, Daniel Deragoni, Concal Wen. But even for this other more complicated guy, we basically have an approximation to arbitrary accuracy for any value of n and for any value of tau. And so then we just take the standard crossing equations and we supplement them with these two integrated constraints, and this now allows us to input the value of tau into the numerical bootstrap, which is very important in order to specify the theory. So before we talk about the non-perturbative results, we can review some perturbative results. So the scaling dimension of the lowest dimension singlet operator is called the Konishi. This has been computed to many different orders in a small coupling expansion, as shown here. Similarly, integrability would allow you to compute single trace operators such as this Konishi at finite lambda, but only to leading order 1/n. Here you see this is subleading order at this order. Finally, kind of the opposite expansion is the strong coupling expansion. So this now works at large n, which you can do with finite tau. For this expansion, you have to use the analytic bootstrap, which involves crossing symmetry but does not involve unitarity. So that's why it's weaker than the numerical bootstrap. And you combine that with localization, and with those two constraints, you can fix the scaling dimension to this order. But you can't go beyond this order. Because if you want to go beyond this order, you need to also use the constraint of unitarity, and that just cannot be used in a strict large n expansion. So this is why you have to do numerical bootstrap at finite n, to take into account unitarity. Okay, so without going into the details, these are the results. So in this first plot, on the x-axis, we have the tough coupling G and mil squared n. The y-axis, we have the scaling dimension of the lowest dimension singlet scalar, which would be the Konishi weak coupling, which is why it starts at 2. And we have these upper bounds for different values of n, computed by combining bootstrap with localization. And so as you see, as n's getting bigger and bigger, we're gradually converging to the integrability result, which is some non-trivial curve until it hits 4, and then it's just a straight line. Because with integrability, double trace operators are just trivial. So it's just 2 plus 2 is 4, and that's the lowest operator once you've hit 4. Okay, so here is a similar plot for the OP coefficient of the lowest dimension singlet. Here, there are no integrability results, so this is just a purely new prediction, which hopefully one day will be compared to integrability. So now, focusing on a specific value of n, let's look at some large value of n so we can compare it to both strong coupling as well as weak coupling results. So here's a plot here. So this was done with different levels of bootstrap convergence, and then we did extrapolation. So the final bound is this brownish one over here. This gray dotted line shows the previous bound by Rastelli and Balt and Chris Beam. So as you see, it's a little bit weaker than the bound you get after using bootstrap plus localization, even at strong coupling. And so the interesting thing about this plot is that you see that it matches the weak coupling results, which is blue at weak coupling, and it also matches the strong coupling results, which is purple at strong coupling. So I think this gives very strong evidence that this upper bound, in fact, is corresponding to the physical theory. Because in every single regime that we can compare to previous results, it matches. The most interesting regime would be in between, because that you couldn't have known from other results. That's a purely non-perturbative result, which we now get from bootstrap plus localization. And
it's very hard to add the theta angle in these computations.
The theta angle, it's a good question. You're just not really sensitive to it. Yeah, so
the Konishi will not.
in this regime, you're not really sensitive to it. Like, I mean, it's incredibly small. So, like, you could add it. I mean, so, like, okay, in principle, this result is taking into account the theta angle. So the purple result, the strong coupling was finite tau, so you're taking into account the theta angle. The weak coupling, you're ignoring the theta angle, but, like, even if you knew it, it would barely affect it. I think the first correction in theta has been computed by people, by Krashensky, I think. But you would barely be sensitive to it.
Because maybe you'd like to hope to also add some kind of constraint from S-duality.
Well, I mean, but we already are doing the constraint of S-duality for the non-perturbative result. So bootstrap localization is automatically S-duality invariant because the input is S-duality invariant. You might be referring to the perturbative results. Maybe you could make them S-duality invariant. So this strong coupling result is S-duality invariant. It's demonstrably a function of non-homomorphic Eisensteins. The only thing which is not S-duality invariant is the blue curve, but that wouldn't really change anything because it's not sensitive to that in that regime. So the most interesting part is this little part here, because that's a truly non-perturbative result, and this is kind of showing level repulsion between the single trace operator in the blue and the double trace operator in the purple. Okay, so here's a similar plot for the OP coefficient. This plot is a bit more striking in that there's a much bigger difference between the weak coupling regime and the strong coupling regime, and you can really see the level of repulsion between the single trace operator here, i.e. the Konishi, and the double trace operator up here. So like you can imagine as n gets bigger and bigger, this would eventually become some like sharp transition. But it's a bit gradual at finite n. Okay, so the last result for n equals 4 is, again, let's focus on this large value of n equals 10, and let's compare to the strong coupling result order by order 1 over n to see that we're really sensitive to these stringy corrections. So the leading order in the strong coupling result, that would be this green curve, which is flat, because we're comparing it, well, I mean, it's basically flat. And so this is the supergravity approximation, which is not sensitive to tau, and it's not sensitive to string theory. The first string theory correction comes in at orange, where you put in the r to the 4 correction to supergravity. So this is sensitive to tau, which makes it a non-trivial curve, and also it comes from string theory, so you didn't know it's from gravity. And then finally, the last correction we know is the one-loop correction, which is also sensitive to string theory because there's some concatenary term ambiguity you had to fix with string theory. And the cool thing is you see is that as you add in each correction, this analytic curve is getting closer and closer to the non-perturbative result. And so this gives yet more evidence that this bound really is capturing the physical theory, and that as we get more and more precise bounds, we'll be able to actually maybe even read off some of these strong coupling corrections. Okay. So that's it for n equals 4. So now a couple words about ABGM. How much time am I supposed to have? 15 more minutes. Okay, great. Okay, so now let's talk about 3D ABGM. So similarly, we look at the stress tensor correlator, superprimaries S, we expanded superblocks. It's a little bit more complicated than 4D. In 4D, we only really had long multiplets because all the short multiplets were trivial. Whereas in 3D, both the short and long multiplets are both trivial. So the long multiplets are here. As usual, we have the dimension and the spin. The short multiplets are what we write here. The short multiplets, their scaling dimension is fixed, but their OP coefficient is non-trivial. And so in particular, we have short multiplets called B2 and B+. We only have those for spin 0. And then we have other multiplets called A2 and A+, and we have those for every spin, either odd or even. And so it's the OP coefficients of these guys that are non-trivial, in addition to the scaling dimensions and OP coefficients of the long multiple. So the way we specify the theory is, again, by the value of C, which now is proportional to n to the 3 halves for ABGM, as well as the value of K, which is the Chern-Simons coupling of ABGM. We're only focusing on maximal supersymmetry, which is why K is just going to be 1 or 2. I should note that for K equals 2, there's actually 2 theories. One's called ABJ, one's called ABGM. Whereas for K equals 1, it's actually a product theory, because there's a free part and an interacting part. We only talk about the interacting part. Okay, so the localization constraints were also worked out. In fact, they were worked out before the 4D case. One of them is actually not an integrated constraint. So if you take 4 derivatives of the mass, then you just get this constraint here, which can actually be solved exactly in terms of the short operator OP coefficients. So the first constraint, the integral kind of trivializes due to this 1D theory, and it's basically just telling you how you can fix these short OP coefficients. Now,
It's topological sector.
it's topological sector, exactly. It's because of topological sector. Now, you might ask, if you have one constraint, how can you fix these 3 things? Well, the reason is that CT itself is fixed in terms of 2 derivatives of mass. And then there's a relation between B2 and B+ due to 1D crossing. So at the end of the day, all 3 of these guys can be fixed in terms of derivatives of masses. It's only the second constraint, there's a typo here, that should be a square. So this, you're taking derivatives of 2 different masses, and this is an integrated constraint. And so for this one, you have to use this kind of new numerical method of combining integrated constraints with Bootstrap. I think the laser, oh no, there it is. Okay, so just as before, the left-hand side can be computed as a function of n and k in terms of some matrix model integral. In this case, there's n squared integrals you have to do. Nonetheless, though, recently it was shown by Nosaka in a very nice paper from a few months ago that you can actually compute this left-hand side explicitly for any n and k. So it's kind of like Nosaka solved a couple months ago, but we're still working on for n equals 4. Because for n equals 4, we have an exact solution to one of the constraints, but not the other one. Whereas for ABGM, we just have an exact solution for everything, which I think is very remarkable. Okay, so now let's show the results from combining Bootstrap with localization. In these plots, the x-axis is 1 over CT. So that means over here, this would be like the generalized free field theory, and then we have like supergravity corrections as we go more to the right. As you see, this x-axis, we're looking very, very close to 0. So we're very much looking at the strong coupling regime. And the y-axis is the OP coefficient of some of these non-trivial short operators. So in particular, the spin 0 guy from A+, and where the left-hand plot is for the k equals 1 ABGM theory, and the right-hand plot is for the k equals 2 ABGM theory. Okay, this is running out of battery. Okay, that explains why the laser's not working. Okay, and we're also focusing on a specific value of n, which is n equals 10. because we want to focus on the strong coupling regime, because we want to compare it to M-theory corrections. And so the cool thing about this plot is that you see that, first of all, you could compute both upper and lower bounds, because this is an OP coefficient of a protected operator. So we actually have islands. So these are rigorous islands. So unlike n equals 4, where we just had an upper bound, and we had to kind of conjecture that the theory saturates the bound, here we don't have to conjecture anything, so we have an island. So the theory has to be in that tiny little space between those two black lines, which I can't show because the laser doesn't work. And so now let's compare that island to the corrections in the large N expansion. And so you see that green would be the supergravity correction, so that's outside the non-perturbatively determined region. And then when you add the red correction, which is one loop supergravity, it kind of moves up and it kind of overcorrects, so now it's too big. But then once you add the next correction, which is due to the d to the 6 r to the 4 higher derivative correction, that lands you smack dab right in the allowed region. And so I think this is a very cool plot, because this is really showing rigorously that this non-perturbative constraint is capturing the M-theory corrections. And so we really are solving the theory non-perturbatively. So this is a much stronger result than what we have for n equals 4 superagnos. And in fact, d to the 6 r to the 4 is the last protected higher derivative correction. So all the higher derivative corrections have been captured by numerical bootstrap so far. Okay, so what's beyond the protected corrections? So ideally we want to learn about the unprotected corrections. So d to the 8 r to the 4 and higher. Because those are the corrections for which people don't know anything. Because there really is no way of computing these things, because there's no world sheet, it's very strongly coupled. So we can't actually use this plot yet to understand d to the 8 r to the 4, because the plot in some sense is like too precise. Because the blue line is within this allowed region, that means we're not really sensitive to the next correction. So we need to look at some CFT data where the plot would actually be sensitive to the d to the 8 r to the 4 correction. So for that, we look at the next simplest CFT data, which is the spin 1 OP coefficient in the A2 multiplet. So this is the next simplest guy. So again, let's focus on the k equals 1 theory. Let's look at n equals 10, where it's strongly coupled. And again, we get this island, which is that black thing over there, that's an upper and lower bound. And we can compare it to the analytic large N expansion, which was known for the CFT data, at least up to d to the 6 r to the 4 order. So again, you see that the green line is supergravity, that's outside the allowed region. The red line is after you add in one loop correction, now it's a bit too high. And when you add in CT to the 7/3, now again it's too low. And so this means that we are actually sensitive to the next correction, which is good. So it's not a contradiction that blue is outside the allowed region, it just means that we're sensitive to the next correction. And so in the plot on the right-hand side, we are testing what the next correction would be. So we're being agnostic about what the power of CT is. And what we learn by comparing the residual, which is basically the difference between the large N expansion versus the numerical island, we find that that difference actually gets the right power of CT, which I think is quite remarkable. So you see that that slope up there is 22.3 plus or minus 0.52 divided by 9, whereas the slope we wanted was 23, and that is consistent with what we're finding. Now, of course, this could become even more precise in the future, so we'd hope to get the error bounds even smaller, and we'd hope to get like right on 23, but I think we're pretty close. And so that means we have correctly predicted the right power of CT, and we can also read off the coefficient, which of course is non-zero. And so I would say that's the most interesting result, because as far as I know, this is the first result about strongly coupled M theory beyond protected terms. So in fact, there was a lot of conjectures in the literature, going back to Michael Green and others, where some people were claiming that perhaps its d to the 8 r to the 4 correction was 0, and I would claim it's not 0. Maybe it would have been more interesting if it was 0.
What was the claim?
I mean, the claim of why it was 0, it was kind of just numerology. I mean, like, there wasn't such a strong argument. Although you should ask Michael. Now, and I should say that we have a similar plot also for the k equals 2 theory with the exact same result, where we can also kind of correctly predict that the power of CT is roughly 23 over 9. Cool. Okay, so those are the results I wanted to talk about. So in conclusion, we find that these bounds from bootstrap and localization give a non-perturbative solution to holographic CFTs at finite n and coupling. So just the complete non-perturbative solution. Now, why do we claim we have this solution? For n equals 4, we only have an upper bound. And so we argue it by claiming that this upper bound matches predictions both at weak and strong coupling. But it's still conjectural in the sense that it's just an upper bound. Whereas for ABGM, we actually have both rigorous upper and lower bounds. We have islands, so in that case, the story is just completely rigorous. So we have just solved the theory non-perturbatively, and as a consistency check, indeed, it matches strong coupling. What's cool about these bounds is that so far they're already accurate enough to read off the lowest few protected corrections from string and M theory to supergravity. And for ABGM, the story is even nicer, and then we have a prediction for the unprotected d to the 8 r to the 4 correction to the M-theory S matrix, which is like the first step into truly, unprotected quantum gravity. Okay, so there's of course many future directions. So the most obvious thing is just to make these bounds more accurate and thus get more unprotected corrections. So how can we get more accurate bounds? Well, there's different ways you might try to do this. First of all, you could try imposing more localization constraints. So one could consider the squash sphere, which might be a dependent. We're not really sure. It's something we've been working on. Another way you could do it, even if it is dependent, would just be by mixing with the lowest dimension long operator, which is also relevant. Because after all, back in the icing model, people might be familiar with the bootstrap plots there. The way they got an island was by mixing all of the relevant operators. Because usually in the bootstrap, you should be including all relevant operators in your external operators. Here, we've only looked at one relevant operator, which is the stress tensor itself. So it stands to reason that by mixing in the unprotected log multiplet, we might get even better bounds. That's just very hard, because there's just many, many Krosby equations once you include the log multiplet, and we hope to do that in the future. Also, this method of combining bootstrap and localization is very general. So you could apply it to any theory where you can do localization. So any 3D n equals 2 theory, 4D n equals 2, 5D n equals 1, as long as there's a Lagrangian, you can do localization. So some other results people have looked at 4D n equals 2 theories that are dual to open strings. So there's been a few papers about that recently. There was a paper about 3D n equals 6, ABJM, so submaximal supersymmetry. In that case, you can study both string theory, M theory, and the higher spin regime. In our paper from a few years ago, we didn't put in the integrated constraint, though. And so in the future, we plan on redoing that study with integrated constraint to get even better results. The long-term goal is that if we can eventually access, so far I've only really been talking about like the lowest operators. If we could access not just the lowest operators, but say like the lowest 10 operators or something, one day as bootstrap technology improves, then we could eventually access operators whose scaling dimensions are scaling like C, i.e. like n squared for n equals 4. And if we could accurately get those operators, those are the kinds of operators that are dual to black hole states. And so then we could study black hole statistics as a function of C and coupling. And I think this is really kind of like the dream of this whole program. Because there's been a lot of work on studying black holes, but always in these kind of like very toy models like JT gravity or SYK, which probably aren't really capturing most of real world black holes. So like the closest we can probably get to real world black holes is like duals to n equals 4 squared mills, where you actually have dynamical gravity, you actually have gravitons, they're actually chaotic, it's not like these exactly solvable theories. And probably the best we'll ever be able to do is from Bootstrap. So that's kind of the long-term goal. Yeah, so in conclusion, there will be a conference in London in December on this subject, which I encourage everyone to attend.
Question? Yes.
Just to make sure I understood, did you predict the numerical coefficient of the d to the 8th
Yes.
to the 4th?
Yeah.
And what is the numerical coefficient?
I don't know. I can tell you later on.
Oh, okay.
I don't know it offhand.
And another question in the case of the ABJM islands,
Yeah.
is there one particular bootstrap constraint that provides tighter bounds relative to other constraints? Like I'm trying to ask if there's a best.
Okay. So what you might be asking is like, what are the constraints you have? So you have localization constraints, which is just like one integrated constraint, and then you have crossing equation, which in principle is infinite constraints, but you look at some finite basis. So you might be asking, in that finite basis of crossing constraints, say in the derivative expansion, are some more important than others? That's an excellent question, and that I don't know the answer, and people have been looking into that. Because indeed, it could be the case that like maybe only like 10% of the crossing constraints are actually doing anything, the rest are a waste of time, and maybe if you just focus on those 10%, then you could do that 10%, but like look at that sector bigger and bigger and get like amazing bounds. I think Ning Su has been looking into that. She's asking more about it, but that's a very good question.
Can I ask for the you want to approach states of n squared also?
Well, one day.
One day. But in this context, I'm not sure what you would compute. What are you going to probe? What are you going to?
Well, okay. So imagine with Bootstrap, you could read off the scaling dimension OP coefficient of long multiplets of very big dimension. And so, if an operator is unprotected, if it's a very big dimension, then you expect it to be dual to black hole state. Because once the energy is big enough, you become a black hole. And so you would ask a question. You would be like, how many operators are there of dimensions smaller than 100, as a function of n and tau?
Of course.
And so what you would expect to happen is that in the weak coupling regime, you would have just some random ensemble probably. But then as n gets bigger and as coupling gets strong, there should be some prediction from gravity for what you should expect.
But you're going to find states of order n before you're going to find n squared, right?
Sure, yeah. So it will take a while to get to that point.
No, but that's already
Yeah.
very interesting states, I would say. I mean, before you go to black holes, those...
Yeah, there are many interesting states. I mean, so far we've only looked at the lowest state. So obviously this is being very ambitious, but I'm just trying to dream.
Other questions? We still have five more minutes. More questions? Yes.
Just maybe you mentioned, maybe I missed it, but do you have intuition what is missing from, for example, for n equals 4 to get islands, or what you have in the ABGM case that you don't have in?
Okay. So let me make sure I make that point very clear. So the reason why we can get an island in ABGM is because there are non-trivial short multiples. So it's almost like n equals 4 is like 2 constrained, because there's short multiples in n equals 4, but their OP coefficients are just completely trivial. They don't depend on the coupling. They're like exact functions of 1 over c. Whereas in ABGM, it's like less constrained, and so as a result, there is data whose OP coefficients are non-trivial. You can compute both upper and lower bounds, because these are operators which are isolated from the continuum of long multiplets, and that's why you can get islands. Now, the way in which ABGM is similar to n equals 4 is that if you attempted to compute bounds on the scaling dimension of the long multiplet, you would not get both an upper and lower bound. You would only get an upper bound. Now, of course, what you could do is you could look at these islands, and you could read off, say, from the boundary of the island, the data, and that would give you some estimate, but that would be non-rigorous. So it just kind of depends on what data you're looking at. It just happens that ABGM has data for which there are islands, and n equals 4 does not have data for which there are islands. Now, one day we want to get islands for the scaling dimensions of both theories. And that would be more analogous to the Ising model. So in the Ising model, the way you were able to get islands is that you had to assume there's only a certain number of relevant operators, then you inserted operators below, and then you can get both upper and lower bounds, and if your bounds are strong enough, they become tiny islands. And so my hope is that eventually such a strategy will be good enough for n equals 4 in ABGM. It's just right now for n equals 4, the bounds are not good enough to be sensitive to the second lowest dimension operator. And that means the bootstrap doesn't really know how many relevant operators there are. And that's why we can't get islands. And so once the bounds get more sensitive, then eventually the bootstrap will know how many relevant operators there are, and then we'll just impose, okay, there's 2 relevant operators, then we'll get islands. And so I am hopeful that perhaps by doing mixed correlators with the long multiplet, which is also relevant, maybe that will improve these bounds and allow you to get islands. But that is TBD.
Okay.
This b to the 8, r to the 4, you say is unprotected.
Yes.
Is it a coefficient? Does it preserve any supersymmetries?
It doesn't preserve any supersymmetry.
0.
Yeah, none. Yeah. That's why it's the most interesting one.
But how much of this have you used the Lagrangian? Could you do this with 2,0 theory?
Okay, that's an excellent question. So the localization requires a Lagrangian, although you have to be careful what you mean by Lagrangian, because of course people do localization for the 2,0 theory, but only for special properties, and that's using the relation between super 8 mils and 5D on a circle and 62,0. So like when they say there's no Lagrangian for 6D, it's not totally true. Of course, I know that you would claim that there is a Lagrangian for 62,0, a non-relativistic one. Okay, anyways, yeah, so like, but there's still stuff you could do for the 2,0 theory. So the 2,0 theory has a 2D chiral algebra worked out by Balt and others, and that's kind of like morally similar to localization, because it allows you to compute things non-trivially. Now, for the stress tensor correlator, unfortunately, the 2D chiral algebra is kind of trivial, in that it's like 1 over C exact, so you would have to look at more complicated correlators, in which case the 2D chiral algebra is non-trivial, and then you really would know additional data as a non-trivial function. So, I mean, this is something I kind of looked into years ago. The problem is just that numerical bootstrap gets worse as the dimension gets bigger. I don't really know why. And so in 6D, the numerical bootstrap just takes forever to converge. And so, like, if you want to look at some correlator other than the stress tensor for which the 2D chiral algebra is non-trivial, we looked at this, 6 years ago, and the bounds were just horrendous. But that was 6 years ago. And so it could well be the case that with, like, updated numerical bootstrap technology, you can get way better convergence, and perhaps you could get, similarly very nice results also in the 2,0, which I think you're working on.
Yeah. So for K equals for 3,3,3,3 in the 2,0 theory, would the non-trivial C dependence allow me to get islands then, or am I?
Well, no. Well, I mean, whether or not you have an island is more like a kinematic statement, because like the island is just like you have an operator which is isolated. And so the problem with 2,0 theory, so for 3,3,3,3 there are some isolated operators, but those are the ones whose OP coefficient you know from the 2D chiral algebra. And the OP coefficients that you don't know from the 2D chiral algebra are precisely the ones that are not isolated.
Okay.
Because those ones live on like this continuum of long multiplets. And so you would only be able to get upper bounds without making any assumptions. I mean, you could also make an assumption. You could say like, okay, maybe there's some gap, and then you can get both upper and lower bounds. But without any assumptions, you would only get upper bounds. But, I mean, that's fine though. Like, you don't need to get an island.
And would you ever consider using as input information that you got from the ABJM case and somehow?
Okay, so that's another excellent question. Yeah, so this is something. Oh, did I even mention that in the future directions? Maybe I forgot to say it. Oh, I didn't. Okay, yeah. So like another thing we'd like to do one day, a dream, is that like 2,0 theory and ABJM in the flat space limit are identical. They're both the M theory S matrix. And this is one constraint which we have not yet used in the numerical bootstrap. And it seems like it's a very powerful constraint because you're basically saying that two different CFTs at different dimensions are actually identical in some limit. And so if you could somehow impose that on the bootstrap, then you'd be able to simultaneously bootstrap both theories and probably get way more precise bounds. I just don't know how to do that technically speaking, because the flat space limit from the perspective of the block expansion is a very kind of complicated, ugly thing. It's like it's basically sensitive to very, very high twist operators, and those are precisely the operators which the numerical bootstrap is least sensitive to. But I think it's really an open problem. So if someone can think of like a practical way of imposing the flat space limit on numerical bootstrap, then I think that would be great. Yeah.
All right, let's thank Shai again.